Hey pre-calculus, I got a new video for you. We've been talking about exponential functions, how to graph them, how to solve equations and inequalities with them. Now is the time in which we are going to talk about the inverse of exponential functions. So what I mean by that is there are inverse operations to pretty much everything that can be done, right? In mathematics, let's say you are, multiplying. The inverse operation of multiply is divide. Let's say you're adding. The inverse operation to addition, subtraction. Let's say you're squaring something. Well, square root it. And that goes the same thing with any other powers in which the base is variable and the power is, or the exponent is numerical. This one aims to set out what happens when we take a specific constant, I lost the word for a second, a specific constant to a variable power. So let's say that you're talking about 2 to the x. I'm like, what the heck is the inverse operation to taking 2 times itself x number of times? It actually shows up in what's called a logarithm. I know, it's very strange, not natural, but here's basically what happens. We've graphed things like 2 to the x power, correct? 2 to the x power can be graphed by just plugging in a bunch of points. So if you plug in 0, you get 1. If you plug in -1, you get a half. If you plug in -2, you get -1/4. And it's never going to go below the x-axis. What a logarithm does is it literally creates an inverse function to the exponential. All right? So when the base of the log matches the base of the exponential, you're just basically flipping the x and the y coordinates. So if to graph 2 to the x power, you went 0, 1, to graph log base 2 of x, you're going to graph 1, 0. If you graphed 1, 2 to get 2 to the x point right here, you're going to graph 2, 1 to get the log. All right? -1 up a half would be over a half down 1. And if there is a horizontal asymptote at the x-axis for 2 to the x, you're going to have a vertical asymptote at the y-axis. This never goes below the x-axis. This never goes left of the y-axis. So this is the log base 2 of x graph. And this is 2 to the x power. They're basically symmetrical over the line y equals x, and they act as inverse operations to one another. So when you apply the log to an exponential that shares its base, they're going to cancel each other out. And the same goes as if you were to apply an exponent to a log, the log and the exponent cancel each other out. So let's see what that looks like in some practical computation settings. Okay? So when I say evaluate each of these expressions, I guess what I'm saying is, can we rewrite the base of this in terms of the base of the log? So log base 5 of 625. Can I rewrite 625 as a power of 5? And from some previous lessons, you guys realized that 625 is equal to 5 to the 4th power. So I'm going to rewrite this as 5 to the 4th power. So here's one way in which to think about it. The log base 5 and the exponent base 5, they are inverses of one another and they cancel each other out. And then all you're left with is the exponent 4, and that's what log base 5 of 625 is. It equals 4. $243. This is 3 times 3, 9, times 3, 27, times 3, 81, times 3, 243, 5. It's log base 3 of 3 to the 5th power. Now there's also a rule that says any exponent up top can be rewritten as a coefficient. That's a property of the logs that we're going to dig into a little bit later. So I can technically rewrite this as 5 times log base 3 of 3. And when the base matches the base of the log matches the base of the exponential, they basically inverse each other out, leaving you with 1. So 5 times 1, 5. Try number 3 on your own. All right, let's see what you got. You're trying to match the base 2 here with a power that can be written as base 2. So think about it. 1/64. Well, 64 is 2 to the 5th power. No, 2 to the 6th power. And if it's under 1, you just give it a negative exponent, and that makes it a legit value. Okay. So log base 2 of 2 to the 6, 2 to the negative 6, those parts are going to cancel each other out, and you're left with negative 6. So I hope you guys are getting like the basics of this. Maybe it's still a little bit muddy in your brains, but the big ideas I want you to come away with today is that that's a real deal thing. That graphically, these two functions are inverses. The log was created to offset, to invert an exponential. It's a man-made thing. Just like most mathematics is, but this was kind of a more bizarre thing. By a guy named Napier, I think. Don't quote me on that. All right, trying a few other ones. Oh, that's interesting. So look at number 4. So what are you supposed to do when the log doesn't match? Can I write 5 as a power with base 125? Maybe? Well, here, I'm going to equip you guys with one more rule that can maybe help out with this. It's called a change of base formula. And here's what it does. Wait, do I want to introduce that right now? I don't know if I want to introduce that just yet. Yeah, you know what? Let's go for it. Here's the change of base formula. If I'm dealing with wonky bases, I can rewrite this as log of any base I want. It seems like 5 is the magic number, so I'm going to go with 5. I can rewrite this as log base 5 divided by log base 5 of the exponential base divided by the logarithmic base. Yeah, that's called a change of base formula. And if you can do that, then you should be able to say, hey, I know what log base 5 of 5 is. It's 1. And then log base 5 of 125 is just 5 to the third power. And then these cancel each other out, and you're left with 1 over 3. So the answer's 1/3, which actually, you know what that does? Is it actually unveils the fact that 5 to the 1/3 power, no. 125 to the 1/3 power is equal to 5. Let's try that same strategy here. We've got 9 and we've got 27. What would be a particularly more helpful base if you're dealing with 9 and 27 for the exponential base versus the logarithmic base? Yeah, it's 3. I heard you back there. Log base 3 of 27 divided by log base 3 of 9. Yeah, with that change of base, it should be pretty straightforward then that 27 is 3 to the third power. And 9 is 3 to the 2 power. So log base 3 of 3 cancels out. You're left with 3 on top. Log base 3 of 3 cancels out. You're left with 2 on the bottom. There's your answer. All right, pause the video. Try number 6 on your own. See if you got the hang of it, or at least with basic examples like this. All right, moment of truth. Sorry, that sounded kind of creepy. Didn't mean to do that. If you're looking at 8 and 16, what power seems to make most sense? 2. If I do log base 2 of my exponential divided by log base 2 of my logarithmic base, I can rewrite 16 as a power of 2 very easily. 2 to the 4th power is 16. Eight is 2 to the 3rd power. Log base 2 of 2 cancels with log base 2 of 2. And that leaves us with 4 divided... Oh, I messed that up. 8 was 2 cubed. So it's 4/3. That's our final answer. So that'll get you through the first 8 examples on tonight's homework. Doesn't seem like they take very long, but again, you got to know what you're doing in order for it to go as smoothly and quickly as that one went. All right, the last thing I wanted to do today is... Oh my goodness, there's 2 more I didn't even realize. That's okay. We can do them. Wow. So embarrassing when they pop up like that. Okay, so what happens when your base is fractional? Well, I mean, as long as you can do change of base formula, it's not a big deal. What base would marry 2/16 with 1/6? Well, as long as you think of 1/6 as 6 to the negative 1 power, you should be fine. Because 2/16 is 6 to the 3rd power. 6 is our magic base. So you're doing log base 6 of 2/16, log base 6 of 1/6. From here, you can change the 2/16 into 6 to the 3rd power. And 1/6 is going to be 6 to the negative 1. Log base 6 of 6 cancels. Log base 6 of 6 cancels. 3 over negative 1 gives us negative 3 as our answer. Now, you guys pause it and try number 8 on your own. All right, the magic base is 3 between 1/3 and 1 over 81. Base 3, base 3. 1 over 81 is on top, 1/3 is on bottom. Hopefully you guys followed me when I did that. Now, 81 is 3 to the 4 power. Since it's under 1, you're going to make it 3 to the negative 4. And then this is just going to be 3 to the negative 1. Log base 3 of 3 cancels out. Log base 3 of 3 cancels out. Negative 4 over negative 1 is positive 4. All right. That was a lot. I did want to get this out of the way, though, before we actually start graphing these logarithmic beasts, because I think it'll be super helpful to just make sure, to just recognize that, hey, the structure we've been talking about persists. It continues with logs. So, your general logarithmic function looks like this. Y equals the negative logarithm of, it can be any base you want it to be. I'm just going to call it a generic base b. Guess what? You can have horizontal shifts inside the parentheses. And you can have vertical shifts on the outside of parentheses. That covers those two. Sorry, that was a little anticlimactic. There are the reflections, though, too. Where do you think the vertical reflections are going to have most power? Or, sorry, I really botched that. What indicates a vertical reflection? That's right, it's the negative on the outside of the log. The negative on the outside of the log gives us a vertical reflection. That negative right there. What would give us a horizontal reflection? It's the negative on the inside of the log. So I'll talk about that more tomorrow, but I wanted to just give you guys a little teensy taste of that as I ask you to build 4 functions with either a horizontal shift, a vertical reflection, or horizontal reflection. All right, I'm pushing 19 minutes on this video. I got nothing else to say. Hopefully you guys make some sense of this, and just please email me or send me a comment in Google Classroom if you need some extra explanations. Thanks for watching.